like that. And you have this magic wand that allows you to change 2 adjacent characters at the same time to whatever it is that you want. And you want to do this the fewest number of times in such a way that you end up with a palindrome, right? So firstly, what we said was that you don't have to focus on both sides of the string. It's enough to focus on one so that you make it look like the other side, and then you have a palindrome. And then what we said was that, so first of all, if this is your sequence, it could be of even length or odd length. So somewhere here is, there may be a middle character or maybe not. But you want this side to look exactly the same as that, but in reverse. That's what you want in terms of a palindrome. And then what we said was that we'll focus only on one side and change things in such a way that it looks like the other side in reverse. And so we don't even have to worry too much about what's on the other side, except to know what to change these characters to. And then what we said was that we will replace this string with a binary sequence, which will tell us whether this character here is the same as its matching partner character. So you'll end up with something that looks like this over here. So this means that the first character is not the same as that character, which means you've got to change it. This 0 means that it's the same, so you could potentially leave it the same, and then and so on and so forth. And occasionally you're going to need one extra character over here because there are cases where it's useful to know what that character is in order for the change to occur efficiently. And we saw some examples of this. Now, here are some basic ideas that I tried to write down, and maybe we can go over them. So first of all, if you look at this string here, this sequence of binary digits, what you'll see is that it's basically a string of zeros and ones, which I can think of as blocks of zeros and ones. So I'll have a block of ones followed by a block of zeros, followed by a block of ones, followed by a block of zeros. And they have to alternate. And each of these could either be of even length or odd length. Okay. Especially, we're interested in the length of the bits that are 1, because those are the ones that need to be changed. The ones that are zeros are of less interest, but we'll see that they're also critical, and we'll see how that affects us. Now, first of all, if this block of ones is even, then it's very easy because I can just take them 2 at a time, flip them to the right characters that I need, and I'll be done. Essentially, in general, because we can flip 2 adjacent characters in one operation, the best you can do is if there are k number of ones here, then the best you can do is k over 2. There's nothing better you can do. So if you can achieve k over 2, go with it, be happy, and you don't need to improve it anymore. So you're going to need k over 2 operations at the, that's the minimum that you're going to be able to do for anything. So therefore, anytime you see 2 ones, if you can change it to 2 zeros, then you should go and do it. Because that's going to generally improve, to help you in the overall analysis. So if you have a block of an even number of ones, then you can just take 2 at a time, flip them to the right characters, and you'll be done with this block of ones, and you'll have 1 less block of ones. Fine? So I don't have to worry about things that are of even length. So the only thing I really have to worry about are the blocks of ones that are of odd length. If they're of odd length, again, what I'm going to do is I'm going to take 2 at a time from that block of odd number of ones until I'm left with only 1 at the end. So essentially, I'm going to just reduce all the blocks of ones. If they're even, I'll just completely wipe them out. If they're odd, I will reduce it to an even number. Fine? So now, in the end, what I'm going to have is not a block of ones, but essentially I'm going to have a 1 followed by a bunch of zeros. Again, a 1 followed by a bunch of zeros, and a 1 followed by a bunch of zeros. That's what in the end it's going to look like, because everything else has been reduced. Are you fine? Okay, so now we have this as our current string, and we have to get rid of all the ones. That's our job. And there's this extra thing at the end where, well, if it's an odd length, you're going to have some character over here, which we don't know. And then we may have, if it's an even one, you're going to need one character over here. So we'll just call this last character as that extra character, and it'll either be 0 or 1. It'll be 0 if it's an odd length one, because if it's odd length, this guy, you don't have to worry about it. Whatever you have there is going to work out fine. We'll just call it a 0 for now. And if it's even length, then we know that this middle character is not going to be there. We just have to worry about whether this character is the same as that character, and it could either be a 0 or a 1. But either you're going to get 2 zeros or you're going to get 2 ones at the end. So whatever it is, you'll be putting something down for that one extra character, and we'll have to kind of take that into account. So this is what our string is going to look like, and our job is to eliminate all the ones in the string, right? Because ones represent characters whose partners are not the same, and therefore they're preventing this string from being a palindrome. So now the question is, what do I do with this one single one that's sitting around, right? And it turns out that now we have to worry about the block of zeros. Okay? If this block of zeros is 2 or more, then, if this block of zeros is 3 or more, how does it go? Yeah, if this block of zeros is 3 or more, then you just have to fix each one separately and be done with it. There's nothing you can do. So this one is never going to influence this one. On the other hand, there are 2 other possibilities. You could have a 1 that's separated by 2 zeros, or there could be a 1 that's separated by 1 zeros. And these are 2 special cases, and everything else will have at least 3 zeros separating the ones. Okay? Of course, there could be more here. All right, are you with me so far? Now, this one here, there's almost nothing you can do other than trying to fix this particular one. And the only way to really do this is to change this 0 to a 1 and then take care of these 2 together. Something along those lines. Okay, so essentially this 1 0, we'll have to change it to a 1 1, which then we can change it to a 0 0. Which is same as saying this 0 will change it so that even though it was right, we're going to make it wrong. And then this guy here, it was wrong in the first place. We're going to flip it, but we're going to flip it to some other strange character. Let's just call it x. And then we would have 2 adjacent characters that are wrong, and we'll just fix both of them, and they will become exactly the same as their partners. Okay? So essentially, you're going to need 2 operations to fix each one of these ones. All right, and there's nothing you can do to improve this because this one is too far away from the next one. Okay? Does this make sense? Do you believe what I'm saying, or you have? Now let's see what happens when you have less. Okay, so these two I call them special cases. If it is something like this, then it turns out the 1, 0, I can flip it to a 0, 1, which means this guy can be made right and this guy can be made wrong in one flip. But I can do that same to this guy here and then flip both of these to the right ones. So essentially with 3 flips I can fix this, whereas here I needed 4 flips to fix these 2 ones. Does that make sense? So 1, 0, 0, 1 would become 0, 1, 1, 0 after 2 flips. And then I can make it 0, 0, 0, 0 in just 1 extra flip. So I'll need 2 here and 1 here, making this a total of 3 flips to fix this guy here. Whereas here I needed 4. Okay. And here actually you can do even better because I can flip 1, 0 to 0, 1. And then these 2 I can flip it in one shot. So essentially in 2 flips I can take care of this. Does this make sense? So I know we're talking about this in a conceptual manner, but pretty much this is these steps are relatively easy. Now, in both these special cases, you're essentially pairing neighboring ones and you're fixing them together. Whereas in this case, there's no pairing that's possible and you just have to fix it independently. Okay? Yeah.
What if I give you like a special, like a case like 1, 0, 1, 0, 1, 0, something
right.
like that?
Yeah. So in 1, 0, 1, 0, 1, 0, that's sort of a degenerate case, right? Here what will happen is that all of these are special cases. And in special cases, you have to pair them up. Here, of course, there are 2 ways to pair them up. And what you'll see is that the leftmost one is going to be stuck anyways. So you might as well pair them in a left to right fashion. So if I can find another one that's close enough, I'll just pair those 2 and take care of it. And so I'll need 2 flips to take care of this, right? That's what this says. And then I will skip over. I'll skip over all these zeros and go to the next one. Now this is the first one that I have. Again, I have a near enough one, so I'll take care of this in 2 flips. So in 2 flips, I'll be taking 2 ones. I'll take care of 2 ones at a time, and I'll be done. Right? So it's equivalent to saying I'm wasting 1 extra flip to take care of this, but if I can merge it with another one, I would actually save 1. That's roughly what it's saying. No? Yeah. And I'm pretty sure of this. So this will take some convincing because here this leftmost guy is going to be left out. So you'll end up paying for this extra anyways. If you can pair it with the next one, you can save some time, save 1 flip essentially. Actually, you're saving 2 flips, right? Because you're saving, otherwise this itself is going to take you 2 flips. But in those 2 flips, you've also taken care of 1 more one. So you're now saving 2 flips actually. So if there is only 1 0 in between, you're going to save 2 flips. Instead, if there are 2 zeros, you can still pair it, but now you'll be saving only one more instead of 1 instead of 2. So now you're going to do, this guy is going to become 0, 1, then this guy is going to become 1, 0, and then you do the third one at the end. So essentially, it's just pairing from left to right, and you can do this in a greedy fashion. I don't think any other smart pairing is going to help you at all. You can pretty much go left to right. If the second one is too far away, you just do the dumb thing of using 2 flips to fix this. That's it. So we've kind of reduced this in a step by step. We first take care of all even blocks of ones, and then we go left to right and take care of ones where the next one is close enough. And we fix that. And there is a simple way to fix it. If it's either going to look like this or like this, if it's neither, then it's the third case. So there are essentially 3 cases we have to deal with. All others are just it's simple pairing, and it's not going to make any difference how you do it. So I don't think this is dynamic programming. I think this is just greedy. That's what I'm kind of convincing myself.
Did implement my solution, which is a DP one?
Yeah.
Did it pass?
Yeah. So DP will definitely work for greedy algorithms. There are DP solutions for most greedy algorithms. But that's all I'm saying is it's probably not necessary here. You could try this greedy one, see if it passes. I'm pretty sure it should. But pretty much all the analysis steps I've told you, I'm fairly sure I can defend it. It seems quite reasonable. Taking care of even number of ones is straightforward. Taking care of odd number of ones and reducing it to 1, 1 is also reasonable. It shouldn't be a problem with that. Then after that, taking care of adjacent ones that are close enough is also quite reasonable. The only thing that could happen is that it could be 1, 0, 1, 0, 1. That's an odd number of these ones, and so there your pairing is not going to work perfectly. So you're going to get one left at the end, and I can assure you that with 1, 0, 1, 0, 1. You can't do that much better. With 1, 0, 1, 0, 1, according to this strategy, this will take 2 flips, and then you're going to need 2 more to take care of this. I tried, and I can't see a way of doing this in less than 4 flips. You're welcome to try this. So 1, 2. And then 2 more, as far as I can tell. If you can do this with 3, then I'd have to rethink everything that I told you. Do you believe this? We forgot to take care of one last case, and that is, remember, we are including 1 extra bit at the end. Now, if it is a 0, then it's quite easy. You really don't have to take care of anything there. But if it's a 1, then you will see that it's an even number of. So if this is a 1, it's because and that's only going to be relevant when this is an even number of characters here. So therefore, this middle character is not there. If this is a 1, this also is going to be a 1, which means that that pair there can be handled simultaneously anyways. And so because you have that extra 1, you will have room to take care of it with just 1 flip. Right? So adding that extra bit is absolutely necessary to make sure you get the minimum. So that should have been there in the first slide here. I forgot to put that in. Yeah. So I should say add an extra bit for a bit at the end. if even length. Something along those lines. I'll try and fix this later. Any questions about this? I know you came in cold, but we kind of discussed this last time. Yeah.
Did you guys get this one on the?
No, this was one of the harder ones. Not many teams got it. Yeah. Okay. Shall we talk about exponent exchange a little bit more? You remember this? This also was kind of complicated. In fact, wasn't alchemy the one that no one solved, or was that something else?
No.
Sorry?
The night one?
The night one, yeah, right. Okay. Hey, Demba. Okay. So this one was tricky. We didn't take care of the general case last time. We briefly talked about the simple case. By the way, if you prefer not to talk about this, I'm happy to talk about range search, although I didn't prepare for that either. What do you prefer?
What was the other one?
Range search, I don't know if you remember that triangle thingy. Yeah,
No, either one's fine.
either one's okay. What do you want to see?
I didn't like this problem.
You didn't like this problem?
Yeah, I was trying to solve it. And my brain started hurting.
You're pissed off with it because you couldn't solve it?
Annoying problem.
Yeah. Yeah. What do you want to see, Demba?
Me?
Yeah.
I think I get the triangle one. I think even we can solve it.
We could try this some more.
Yeah, maybe this one.
Okay. All right. Okay, so were there examples here? Yeah. Right. Okay. So let's look at this example, and maybe I haven't quite thought about the general case, so we'll see how things go. So first of all, it says that the value of b is 10, which means that each digit or each how does it even go? So think of that as the base for your digits, right? So this could be anything from 0 through 9 because the base is 10. And then it says that there are 5 digits in the number. So b is equal to 10, p equals 5, and the number is, so this is the number that Alice has. She has 42786. So she has, just think of this as $42,786. Now Bob is, you know immediately how much money he has because the sum of Alice and Bob is simply 100,000. Okay, that's what you're told. You're told that their sum is p to the b, right? Or is it b to the p? B to the p, yeah, b to the p. So 10 to the 5. Okay. Right. So that's this number. So therefore, you know exactly what this is. It's going to be 4, 6, 10, 1, 8, something like that, right? And now you are, either of them could send money to each other, but in installments of a, what was it, a power of 10? I forgot.
Or
B to the
B.
power of y.
Yeah.
Power of b.
No, B to the power of y.
B to the power of y, I see. So it could be, yeah, so it's a power of 10 in this case, right? So 10 to the power something, 10 to the power x is what they can send to each other. Which means that if Alice sends a power of 10 to Bob, then it will either reduce 6 to 5, 8 to 7, 7 to 6, 2 to 1, or 4 to 3. One of these digits will get reduced by 1, right? So if we look at this first column here, then essentially it says that if Alice were to send the money, it would take 6 transfers, whereas if Bob were to send, it would take only 4 transfers, right? Over here, if Alice sends the money, then it would be 8 transfers, whereas here it will be only 1 transfer for Bob. Now, remember there were sort of 2 versions of the problem we talked about. One is if we wanted to minimize the total number of transactions, then all we have to do is to take the smaller of the 2 digits and just add them up, right? So it would be 4 plus 1, 5 plus 2, 7 plus 2, 9 plus 4, 13, and 13 transactions. All the money would be, right, all the money would be with one person, right? Well, we have to be a little bit careful because when the bits get transferred, when there's a carryover, some of the numbers could change. In fact, at the end, it doesn't matter who sends the money to whom. Right, so if all we care about is the number of transactions, it's kind of easy. But if it's not, then it becomes a little bit tricky. And so what did we say about this? It was a lot easier to think about this when the numbers were binary than they are when they're decimal. We could try and work this out in the binary case and then carry over to the decimal case, or we could try and do the general one. Yeah.
So one thing that I noticed is that if you start from the first
The
number
least
that's
significant,
different,
yeah.
You can, let's assume B is getting all the money.
Yeah.
You have 2 options. You can either send A's monies to me,
Yeah.
and then I have a carry bit,
Yeah.
or I send my money to A, and then A gets a carry bit.
Right.
And at every point, the sum of the digits is always
The
B.
same. Sum of the
sum of the top and the bottom.
right.
Always be
Correct. Will always be B. Right. Sorry. Will always be B.
Yeah, B.
Right.
So maybe you can do some dynamic programming with that.
I see.
You have 2 options. You can either send this money or.
Right. So if you use dynamic programming, will you need a 1-dimensional or a 2-dimensional? I guess you just need a 1-dimensional, right? Yeah. So let's say let's call d of I to be the number of transfers that would be needed to make the ith digit and everything to its right to be zeros. Okay.
Number of transfers, you mean the minimum number of transfers, or?
Well, no. Yeah. That's right. So we have to be clear about that. Well, if we have to take something more into account, then we'll need a 2-dimensional.
That maybe keep track of
How many?
one person and then you can find the minimum for
Can I
that?
ask, what does it mean when it says the busiest player must initiate?
Yeah, it means that if you say that Alice transfers 17 times and Bob transfers 18 times, then the busier person is Bob.
So fewest number of transactions?
No, it's not the fewest number of transactions, because if it's fewest number of transactions, we know exactly the answer.
Okay.
In fact, for each one, you just send the smaller one sends above. But if all these digits were smaller, then Bob would just get too busy and Alice would have nothing to do. So you want to distribute the work in such a way that Alice also sends occasionally a little bit and see if she can reduce Bob's work. Okay. So you're minimizing the maximum number
Okay.
instead of always minimizing the sum. So in fact, we can count the total, that the minimum number of transactions that we have, and maybe work with that. So in the minimum one, right? We know that this one's going to send 4 plus 1 5, 5 plus 2 7, and so Bob is going to send over 7, and Alice is going to send over 3 plus 5, that would be 8. Right? Is that right? Because when you send 4 over, this is going to become 9. And then you send 1 over, so that's 5 cents now. Then you send the 2 over. So you've sent 7 so far, but then all of these would have become 0 by then, and this would have become 3. Then 3 gets sent over, and then, it's not 8, it's 7. So it's already 7 and 7. This is the best. I don't think this can be improved anymore. But you have to think about the case when that's not so. So imagine the case when we flip these two. Let's make this as 57 and this as 42. Okay. If this were the input, then what you'll see is that in order to minimize the total number of transactions, you're going to send 4 plus 1 5 plus 2 7 plus 2 9 plus 4 13. So you're going to have 13 transfers for Bob and 0 transfers for Alice. And this is not considered an optimal answer, even though the total number of transfers is the absolute minimum. In fact, anything else you do will end up with 14 transfers in all, but it'll be more balanced. And in fact, we found a way to do this 7 and 7, right? So we have to see if that's possible. Well, think about it this way. If Alice did the first 6, then you can reduce Bob's transfers by 4. So you would have 6 for Alice and 9 for Bob. Is it 9 or 10? I'd have to think about this. So if 6 is sent over, this becomes 2. So then you would have 2 plus 2 plus 2 plus 4. So it would become 10 actually, not 9. Does that make sense? Or another option is to wait for the end. This also is going to become 6 and 4 there. Anything else you send will end up tipping the balance too much, it seems. Is this the best answer here?
So can I ask, so every digit as you move from right to left, you're comparing what if A sends it, what if B sends it, how does it affect the total transactions?
Right.
You're choosing the right one and you're moving left to right.
Correct.
Right to left.
Correct. roughly speaking, yeah.
What if A sends 5 at the end?
Well, it's not going to be 5 because if B is sending, this is going to become 6.
Then 6 and 6. Then 6 plus 6 is 12. It's still smaller than 13, right? And
It is smaller than 13, but then your maximum would be 12, not 10, not what Bob
The
sent.
maximum is 10 already. Okay.
Right.
Okay, I see.
Yeah. Yeah, looks like I don't see this being improved anymore, but maybe, yeah. Yeah, I just don't see it improving anymore. Fine. So that brings us to the dynamic programming. So what is D of I? Oh yeah. So first of all, do you believe that we should be going left to right to left? Is that clear to you?
Yeah, it makes the most sense.
What's wrong with starting from the other end?
How would you handle the carrying bits if you start from the other end?
You just have to do an extra transfer at the end. No, I'm kidding. Maybe so. Maybe so. All right, fine. So let's assume that we're going right to left. And for each one, it doesn't make sense for both of them to send. So it's either A or B for sure. Right? Either 6 is going to be sent or 4 is going to be sent. So we know it's just those are the numbers to be dealt with. And over here, it's either going to be 8 and 2 or 9 and 1, right? So it's just a matter of,
Do you want to avoid having a carry bit?
you cannot avoid a carry bit. You
So,
have to make them zeros. Remember, in the end, you want this with one person.
well, for example, if that was a 9 up top, and you transfer a 9 over.
You can't have a 9 on top, because if that's a 9, this is going to be a 1.
No, on the left side. So if that
If this were a 9, this would be a 0.
Oh, okay.
Because that's how the numbers are complementary, because they have to add up to the number on top, right?
The difference between A and the initial is the bottom.
And then, so you're saying the difference between this number and this number? Oh, difference between the 8 plus 1 and the,
No, I was just telling him why.
oh, you're telling him, sorry, I thought you were giving me an answer. Okay,
A
fine.
is like the difference.
I thought you had the problem solved.
I mean, it's easy to solve for if we were just minimizing the cost, because then it would just be the 2 options and the minimum.
Yeah, I know.
Yes.
If we are always trying to, if at every step we are trying to optimize the number, the difference between Alice and Bob, then it's easy. But I don't see that as necessarily the right way.
Yeah.
Because maybe later on you have to really, you could do things better. Right?
If we expand the TP state to include how many operations, like let's say Alice has done,
Uh-huh.
and we try to minimize how many Bob does from that state. And then
Well, we can always minimize the difference, right? Because the optimal one will have the least difference, for
Yeah,
sure.
But I'm saying, like, for a certain number of operations that Alice does, I want to find the minimum, and then at the end I can just maybe iterate through
But I'm
Bob.
saying, what if I want to keep accumulating Bob's cost, and then after that I'm going to just do the opposite or something like this, right? Whereas we're always trying to optimize the difference right at the start, and I'm saying that doesn't have to be. It's possible that Alice pays at the start and then Bob pays, or the other way around, or maybe it's some strange mix of the two. So the way I had done this before was I started from 13 and I said, how do I reduce this? And in order to reduce this, I am going to pay with the smallest of these. So I was just going to go with the smallest over here. And in this case, it's actually a 5, but I don't know how to take care of the carryover. So I would have started here, and I would have said at this point, you let Alice do some lifting. And at the end, you just have all 6 go over here. Okay. So that's how I would have gotten the A not over here. So that would be the first, and then I would take this as the second if it's needed and if it would help, and then this as the third, and so on and so forth. So we could try different numbers and see if this works out. Yeah. So let's say we have 5, not 5. Let's say it's something like this. So that means this is going to be 4, 4, 3, 4, 3, right? So I would look at this and I'd say the smallest one is one of these two. It doesn't matter which one. And I would earmark. So I would first of all I'd find the worst that you can do, which would be this sum is smallest, so 12 plus 6, that's 18. So 18 transfers, and this would be 0. Right? So then I'd say, okay, this one is the smallest among the larger ones. Sorry, among Alice's digits. And so this guy here, I'm going to target it for sending down instead of the other way around. And if that happens, then I would get, so this would get reduced by 4, so it would become 14, and this would become 5. Is that right? No, actually it'll be 6, right?
Maybe 15.
It'll be 6, and this would be 13, I think. Because it's 4 plus 4, 8, 8 plus 6, 14. It is 14, is it? Wait, so 4 gets transferred. This becomes 6, 6 gets transferred. This becomes 4.
So 4 gets transferred.
So 4 gets transferred. Actually, I added this wrong then, right? Because 4 gets transferred, then, oh, I see. What if I sent all of these? No, this is 18 is correct. Okay, fine, fine.
Should that be 14 or 15? Because if you send the 4 up for case 1.
If I send 4 up,
Yes.
then this becomes 6.
And then it sends the 6.
6 sends down.
This becomes 4.
Then this becomes 4. Then it would become 4 plus
4 plus
4 plus 4, 8. 8 plus 4, 12, and 3, 15. You're right. Okay, fine. So for every switch, it seems that I may have to add one extra. It's right. That's what it seems like. Okay. Yeah. So let's say this is right. Now we're trying to improve this even more, and I take the next smallest, and the next smallest is this guy here. So I target that, and this time what will happen? So this will become 15 minus 4, 11 plus 1, 12. That's what it seems like. Let's hope that's correct. And then this one would become 6 plus 6. That would be 12. And it looks like this would be the best you can do. So let's check if this is right. We've got 4 going over. So for Alice, it would, sorry, for Bob, it would be 4. This one comes down. This 4 goes up, so that's 8. Then this guy comes down, and then this 4 goes up, so that's 12, right?
Yeah, I think it makes sense because regardless of.
So it seems like a greedy algorithm. I don't see a dynamic programming here also. That's my that was my problem with when I dealt with the binary case.
It makes sense because A, you always want to choose the.
You always want to choose the smallest one that will try to get us there, right?
And the cost of choosing anyone is the same.
But here is where I was having some doubts. What if ultimately we are trying to even this out, right? What if we so here somehow we had 5 plus 5, 10 plus 2 extra that we get to become 12. What if I had a 11 here somewhere? I know 11 is not possible, but let's just imagine this, right? Then what if I took that instead of trying to distribute it over many spots? So is it possible that taking just one large number is better than 2 small ones? I wasn't quite sure of that. So that's where I was having some trouble, and I was hoping you guys can think about this.
It may be possible.
Because ultimately, is it like a knapsack where you just want it to be the right number, and so you're picking the right numbers in order to make that sum, or are you just looking for small ones to take, right? If, for instance, so let's, instead of 5, let's change this. Let's change this to.
If you had an 11, the cost would be the same.
Let's change this to 6. I think 6 itself will make this look different. So let's restart this. Yeah. So again, this would be 0, and this would be 8 plus 6, 14, right? Sorry, 8 plus 9, 17. What am I saying? Fine. Now I'm saying I'm being greedy and I'm sending this over, and that would make this 6, 17 minus 4 plus 1, right? 4 plus 4, 8 plus 6, 14. And I'm thinking this is this is not quite the best you can do. Because now if I take one of these, it will send it over. So I'll get, well, if I send this 6, then it's actually a little bit less. So maybe when I do greedy, I should think of these as something plus 1. That's really what it means. So I'll send this 6 over, in which case I would get 6 plus 6, 12 here, and I would get 14 minus 4. Is it? This is what it seems like to me.
Maybe 14 minus 4 plus 1.
Because it's the last digit, I don't think so. I'm hoping not. Oh, yeah, because then this becomes 4, 3, 3, and that would be 10. So here is then my solution. Let's redo this. Here's Alice, here is Bob. Doesn't matter what these digits are. Firstly, you add the digits, figure out which one is smaller, right? That's going to tell you this. So this is going to be the sum of the digits, whatever that is. And let's assume Bob is the one who has the larger one. So then, the smaller one. In that case, it would be beneficial for Bob to send over if your goal is to minimize the total number of transfers, right? So then, what we're going to try and do is to greedily make this more even. If that were the case, then what we would do is find the smallest one on Alice's side. So for Alice, let's say the bits are A1, A2, A3 up to AD. So we're going to make a list that has all these guys, AD, AD minus 1, up to A1. But for all these middle characters, we're going to add 1 because there's going to be there should have been a carryover, right? So in each case, we'll look at this and we'll say which is the smallest. And we'll make that one as something that Alice is going to transfer rather than Bob transferring. And then we keep doing this until the difference is minimized. That was my suggested solution. I'm not sure it works. What do you think?
I'm thinking there might be a case where it's not optimal to do that.
Yeah.
But it's hard.
I couldn't quite prove. I tried proving this and I couldn't. So let's assume that the optimal solution involves taking some of these guys and having Alice transfer instead of Bob transferring. Okay. What if they are not the smallest ones, right? Only then it wouldn't be the optimal. Yeah. Okay. So if we want to DP, then what do we do? D of I.
Wait, did you find a proof that this doesn't work?
Well, so for instance, I'm thinking of the case when the next smallest puts it way over. Okay.
One of them means the bigger ones.
Right. So and maybe if I had taken a bigger one earlier, I would have made it closer. That's what I'm thinking. Yeah. Now the greedy strategy will get us close, but it may not give us the optimal answer. So let's go back to the dynamic programming. Let's see how we want to set this up. In each case, every time you look at a bit, there are only two choices. Either Alice sends to Bob or Bob sends to Alice. And we can write down the two possibilities, right? So DI is really the minimum. Well, we don't know what the minimum is. It's either Damn it. What are we trying to optimize here?
If you had a lot of memory, you can just store what Alice has and what Bob has.
What they have is a one-dimensional array. That's not a problem.
No, I'm saying for the DP state. You have
You can't store all the actions on the other bits, because that would be if there are d bits, then it's going to be 2 to the d options. That's not going to happen.
I don't care about the options that they take. I just care about the sum.
Right, but then at each point you have to choose. So let's say that Alice did send it over, but there may be multiple choices for what happened earlier. I don't know which one of those to pick.
You try both.
It's
The
not
only-
both. If it were only 2, I could try both, but what if there were many, right? So here's what I'm saying. My tree of choices is, let's say, for the nth bit, for the dth bit, which is the, okay, that's the least significant bit, fine. Either Alice sends or Bob sends. Then for d minus 1, again, I have Alice sends or Bob sends, right? So I'll have this tree of choices. If there is a way to pick one at each stage, then I would have only one from each side, and I can make that choice here. But I don't know why I should pick one or the other.
You try both, but the thing that
It's not both.
overlaps-
Again, you keep saying both,
Yeah,
but actually there's whole bunch of choices that I made here, and all those are sitting here. Which one of those should I pick?
what overlaps is that I only really care about the sum of both people and who has the carry bit.
No, what I'm saying is the following. There are, of course, many choices I made. And each one had a different set of choices I made for the let me flip this around. This is not the dth bit. Let's say this is the first bit, right? Meaning it's the most significant bit. This is the second bit. This is the third bit. Somewhere here is the dth bit. And I'm saying all the choices I made here, of those, which one should I keep here? Then here I can say I can try both. But here I have 2 to the d minus 2 choices. Which one should I pick? Which one should I keep?
What I'm saying is that you may not have, so there may be a bunch that are overlapping, like it's not necessarily disjoint. The right side may have the same state, and the number of states isn't exponential.
Okay, let's take a real example, right? Let's take the example that they have in the paper. Can you read that number for me? 4.2.
786.
So we had this. We had this, right? I'm saying that here we made one choice, Alice or Bob. Here we made one choice, Alice or Bob. Here we made one choice, Alice or Bob. So when I got here, I have 8 choices I could have made for all of those. And then I have to decide on the choice here. Okay, so here I have 2 choices, either Alice sends or Bob sends. But for each one, which one of these should I match it with? I can't keep all 8 choices. Because if I did, then I would have exponential number of options. So of these 2 to the 3 or 8 possibilities, tell me which one to pick, to keep. or at least which two to keep. I don't know what that means.
You don't know, but you just try both. But the recursive.
But again, you keep saying both, but I have 8, not both.
Yeah. So at the recursive tree, we try both. The only thing is that because of DP, we don't have to compute all exponential options. A lot of them are overlapping. If I have the ith bit.
No, the thing is that the choice here for Alice or Bob to send is completely independent of the choices there. And there were 8 different cases. Each of those has a different cost. I'm asking which one should I consider the best for me to consider over here. How do I make that decision based on the decisions here?
Should we consider the one that minimizes the difference?
That's what I'm not sure, because it may be that here I should let the difference keep going higher and higher, and then worry about it later because I have the right numbers later on to fix it. It's possible that the optimal answer is that over here only Bob sends and over here only Alice sends.
For example, if you had 9, 9, 9.
Well, in this case itself, in fact, it turns out that these 3 Bob sends and these 2 Alice sends. In fact, that's the best, if I remember correctly. Now, why should I pick Bob sending instead of Alice? And in fact, it's only increasing the difference. It's not like it's decreasing the difference, right? Because I started with 4, then it became 6, then it became 9. And in each case, it turns out that those were actually optimal choices. I didn't know until later that they were optimal choices. Sorry, it's 7, not 9. Yeah. Here there were 2 choices, Alice and Bob, and when you came here, you could consider both those cases. But then when you come here, you already have 4 choices, and you don't know which ones to consider as the ones to decide to make the decision for this. And it turns out, so maybe we should go this way. Let's see. So I think that dynamic programming has to be 2-dimensional, and we have to keep track of something else, which would be the difference. All right, let's see if we can do this.
What if it's possible to do this? We already know how to calculate the total cost, right? So since we already have the total cost, we already made a bunch of decisions in order to get that total cost. And then what if we go back and now the ones that we didn't choose, we now consider, okay, what if we chose this and alter the total cost and make that our
Yeah.
state?
I think that's roughly what will happen here. So let's see. I have decisions to make. So let's do it in the reverse order. D minus 1. Okay. This array, let's call this the D array. D of I comma j. So in the ith row, we're assuming that we've made decisions for all of these I bits.
The optimal decision.
Optimal decision. Well, not optimal.
Not optimal.
It is optimal, but we want to achieve a difference of j.
We want to achieve a difference of j.
Yeah. Okay. So we want to say decision for I, for bit I or digit I, to achieve a difference of j. Okay. So think about the first decision. There are only two possible things you can do. One is either achieve a difference of 6 or achieve a difference of 4. Everything else is just not going to be possible. Right? So no decision for, so let's actually write this down to, there's more, but let's not worry about it. So let's say that we can achieve a difference of 6. We can achieve a difference of 6 if Alice sends, or we can achieve a difference of 4 if Bob sends. Are you okay with this? Okay. Now let's try to make a decision about d minus 1 and see which differences we can achieve. Only these differences are possible. So if we already have a difference of 4, if Alice sends 8, sorry, this one would have become 9 now, right? So that's 9 already. If Alice sends, it's going to be 9 minus 4, 5. So we would have Alice here. And if it were yeah, this one is connected to that, or if Alice is done on top of this, it's going to become 6 plus 9, which is 15, which is too high. So we would also do something on 15 here, and that would be Alice. But now we would have a bunch of A's. That's not good. Yeah, that's fine. So let's assume that we can achieve 15 with Alice sending here or Alice sending here. But if if Bob sends, it's going to be oh. So that depends on who sent the thing earlier. So oh dear, this is not good. Not looking good. So difference of 4 or difference of 6 is possible. But with the difference of 4, it would be Bob who would have sent it, which means Alice's digit would have become 9, and this would have become 1. If, on the other hand, Alice had sent, then this 6 would be here, and this would become 2, and this would become 8. So we have to deal with these differently depending on what we get. So over here, we're going to deal with either 9 and 1 or 8 and 2. So if it was a difference of 4, well, we'd have to differentiate between minus 4 and plus 4. This is kind of annoying. Okay. Let me redo this then. Let me draw it the following way. So this is the dth bit. This is d minus 1 up to 1. And somewhere here is a difference of 0. And then we have minus 1, minus 2, minus 3, etc. Then we have plus 1, plus 2, plus 3, etc. So at the dth bit, so let's say this is Alice minus Bob. If Alice sends, it's going to be plus 6. And if Bob sends, it's going to be -4.
If Alice sends is +6, if Bob sends is -4. Why are we choosing -4?
Because we're doing number of moves of Alice minus the number of moves of Bob. Okay? No other thing is possible. And now we're saying, should Alice make the next move or should it be Bob? And we're looking at what things will get populated here. So if Alice sends on top of this, she would be sending, because Bob sent the earlier one, Alice would have 9, which means that it would become 9 minus 4, it would become 5. So somewhere here for 5, you would have Alice. And if Bob sent over, this -4 would become -5. Right? At the same time, you would have for for this one here, if Alice sent on top of this, it's going to become 6 would have gone plus 8, so that would be 14. Somewhere down there would be 14. And then this would be, anyways, you see where I'm going, but I need to look at the numbers. Is this even going to work out? How big are the numbers allowed to be?
The number base is up to 100, P is up to 1,000.
P is up to 1,000. Damn it. That looks 10 times 1,000. It's okay. So that's still 10,000 by, so this is going to be of length 20,000. And that's going to be of length 100. That's a lot, right? 20,000 by
20,000
and
D would be 1,000, right?
D is 1,000.
Yeah, because that's what P is, right?
That's what? No.
Because we're going by the digits.
Yeah, we're going by the digits.
So
Yeah, that's
gonna be
P.
1,000.
That's 1,000.
Yeah, I think that should be fine.
20,000 by 1,000 is okay.
I believe so. Maybe 20 million?
So 20,000 by 1,000.
Yeah, you're right, 20 million.
Sorry? Okay, let's say it's okay. Then can we now solve the problem is the question. So for each entry here, we're going to get 2 entries in the next one, and so on and so forth. And that's what I'm trying to get at. If we take it from a B, you would get a different set of values. If you take it from an A, you'll get a different set of values. And if you have both A and B somewhere, then you can take the smaller of the two. Let's try and work on it, see if we can solve this next time. We got to figure out the dynamic programming recurrence relation. Thanks. You were
Might be
saying
good.
a dynamic